Alright, number 17. As a wave enters a medium of higher refractive index, so that there is our n value. That is n. So if n goes up, what happens to the wavelength? Goes down, shortens along with its speed. So here we're gonna see choice A decreases. Ooh, someone just got killed. That's Game of Thrones for y'all. Okay, 18. One vibrating 256 Hz tuning fork transfers energy to another 256 Hz tuning fork, causing the second tuning fork to vibrate. This phenomenon is an example of resonance. Let's do that in purple. Resonance, guys. So if you have this tuning fork vibrating, it's going to transfer energy into the other tuning fork because it's going to vibrate. It's the same natural frequency. So this is going to vibrate too. And this is what we call resonance. Alright. Okay, so this here, number 19, we have two waves, a crest and a trough, meeting together at point X. So we have a crest plus a trough. What does that equal? Destructive interference. Okay. When that happens, we're going to subtract their amplitudes. So for crest A, it's a positive 2. Crest B is a negative 1. So plus 2 and negative 1 equals positive 1. Alright, number 20 is talking about the Doppler effect. So we have a moving source. We're going to figure out what happens to the frequency and wavelength of the radio signal. So Doppler effect, toward, frequency goes up, wavelength goes down, away. It's the opposite effect. Frequency goes down, wavelength goes up. Alright, in this case, number 20, it's traveling towards Earth. So compared to the frequency emitted by the antenna, the received signal, so the observer is the receiver. So the observer is going to have a frequency that is higher because we're going towards. It's going to be higher frequency and shorter wavelength. There we go. 21. Alright, 21. A periodic wave having a frequency of 5 Hz, so f equals 5 Hz, speed equals 10 meters per second. What is the wavelength? Lambda. V equals f lambda. 10 is equal to 5 times lambda. Lambda is equal to 2 meters. Choice B. Number 22. If the frequency of a periodic wave is doubled, if frequency goes up, the period goes down because they're inverses of each other. Alright? So that means if this goes twice as big, this is going to be half as big. So it's going to be half. Next, number 23. What is the period of a sound wave having a frequency of 340 Hz? So frequency is 340 Hz. We're looking for period. So they're inverses of each other. Period T is equal to 1 over F, which is 1 over 340. That should be approximately... You should get approximately 2.94 times 10 to the negative 3 seconds. Choice D. Alright, number 24. As a wave travels through a medium, the particles of the medium vibrate in the direction of the wave's travel. What type of wave is traveling through the medium? Alright, so particles vibration in the same direction of waves travel. So, direction of travel is equal to our vibration direction. If that's the case, that means they're parallel. Therefore, parallel. What kind of wave is that? It's a longitudinal wave. Alright? As an example, this here is our longitudinal wave. The speed of the wave is moving this way. The particles themselves will be vibrating back and forth this way. Transverse, on the other hand, will be like this. The speed of the wave will be going this way, whereas the oscillation, the vibration of the particles will go up and down. That is perpendicular, transverse. Okay, number 25. What is the current through a wire if 240 coulombs of charge pass through the wire in 2 minutes? Okay, current I is equal to Q charge over T time. 240 coulombs is equal, oops, oh my gosh guys, I'm messing up here. Our current, is equal to 240 coulombs charge over, what is our time? 2 minutes. 2 minutes is our time. But we got to convert that to seconds. 2 minutes is 120 seconds, so over 120 s. And that is equal to 2 amps. Okay, 26. We got to find equivalent resistance REQ. But the formula for finding them is different between a series and a parallel circuit. So in a series circuit, you got to add them up. Like this, R1 plus R2, etc. In a parallel circuit, it's the other way. It's that inverse fraction stuff. Like this. You gotta add up the fractions and flip them and such. So we gotta figure out which of these is equal to 6 ohms. We're looking for REQ is equal to 6 ohms. Let's look through each of our choices and find out which of them will add up to 6. So, as a side note, in the series circuit, REQ is large, it's big. In our parallel circuit, we're going to have a small REQ. So if we're looking for 6, we can knock off our choices B and D, the parallel circuits. In A and C, there's series circuits, so we could simply add them up. Choice A is 5. Choice C is 6. Choice C. Number 27, what is the equivalent resistance of this circuit? What type of circuit do we have? It's a parallel circuit. How do you know? You look at these branches. So if we gotta figure out the equivalent resistance, we got 4 resistors here. So we gotta go all the way up to R4. Alright? If you plug in these into the calculator, it's pretty simple using the inverse button. But if you want to do it by hand, I'll show you how. First, we got to find our least common denominator. And for all of these numbers, it just so conveniently works out that it's 36. So 1 over 36 becomes 6 over 36. 1 over 12 becomes 3 over 36 plus 1 over 36 plus 2 over 36. Add them up. Six plus 3 plus 1 plus 2, that is 12 over 36. But we're not done here. We gotta flip it. Which is equal to 3 ohms. See how a parallel circuit reduces the overall resistance? That is our ideal setup for nowadays. Okay? 3 ohms. Okay, so here we have a ray diagram. A light ray is traveling from water to air. We're not used to seeing going from bottom to top. We're typically seeing it top to bottom. But for this one, it's bottom to top. Because how do you know that? You gotta look at the arrowhead right here. That tells you the direction. And this is the incident ray. If it's pointing inward, this is the incident ray. Alright? and it's coming in at an angle of 35 degrees. Number 28 asks, identify one characteristic of this light ray that is the same in both the water and the air. So, what doesn't change? What doesn't change about light when it travels between mediums? Well, speed changes between materials. Wavelength changes between materials. But what always stays the same? The frequency. Whoopsies. The frequency stays the same. We gotta calculate the angle of refraction of the light ray as it enters the air for number 29. And we gotta show all work. This means we gotta use an equation, guys. Calculate for the angle of refraction. So this means we use Snell's law. N1 sine theta 1 equals N2. My mistake, guys. N2 sine theta 2. And 1 for water, because it's the incident medium, is 1.33, and air is 1.00. So here we substituted in 1.33. Sine, our angle here that corresponds is 35 degrees. Air is 1.00, and we're looking for that theta, sine theta 2. Theta 2 then. Do not forget we're doing sine function, so we got to take the inverse sine. You put it into the calculator. This is how it should look like. Okay. Okay, when you plug it in, you should get an angle of approximately 49.7 degrees. When you round, it's going to be about 50 degrees. Okay. Alright, number 30 asks for the angle of reflection of the light ray at the interface. It is always equal to our angle of incidence, which is 35 degrees. If it goes in at 35, it bounces back at 35 degrees. Alright, and then we have to use a protractor and straight edge to draw the reflected ray for number 31. Should look approximately like that. To be honest, if you're going to do this on a test, you should really use a protractor to measure it out. This is my very lame attempt at replicating it. It's almost there. And that is it for this review question. Please note, you're probably going to expect seeing a short answer question just like this one. So make sure you know how to use that protractor, guys, come the test. And that's it. Take care, guys.